Okay, people, I think we'll start. The others can join us. Any questions so far, comments, and particularly on this, the solution to this numerical question?
Can we go through this example?
Okay, so we are interested in finding the Gibbs free energy associated with electron transfer from oxygen to hydrogen peroxide. Abbas? Okay, we are interested in finding the Gibbs free energy associated with electron transfer from oxygen to hydrogen peroxide. So, when there is an electron transfer, there is energy associated with electron transfer. That is the basis of all our batteries and so on and so forth, all chemical to electrical energy conversions. The electron transfers in the cell are capable of providing energy to the cell, right. So, the solution was as follows. We have information about energies in terms of the reduction potentials. That is what we said. And before that, we need to be clear about how it is formed, the details of it being formed reaction wise. Hydrogen peroxide formation from oxygen can be represented by this equation, right. So, oxygen plus 2 E minus plus 2 H plus giving you hydrogen peroxide. We do not have information on this, but we have information on the conceptual half reactions that make up this whole reaction. So, the conceptual half reactions and the standard reduction potentials from the table. There is a table that is given on your Moodle page, you can check that. This will have the values for these. The standard reduction potential E naught at pH 7 was minus 0.33 volts. Okay, we are worried only about pH 7. The standard value, no life exists, therefore, we are worried about E naught dash, and that is minus 0.33 volts here. This value is directly from your table. Then the other half reaction is this superoxide giving you hydrogen peroxide, right. So, in this case, the standard reduction potential at pH 7 is plus 0.94 volts. So far, so good. So far, your
The E naught dash value for both of these reactions.
okay. Can you open up your Moodle page? So, there you will find this, right.
So, what reference did we take so for each reaction?
So, the half reaction is represented as this pair. Remember the where did we say that? Yeah, this is fine. Somewhere we said the slash representation. No, then we come to this example. We might as well look at the table here. That might. See here, for the reaction is represented by a couple. For each couple, the oxidized species is on the left and the reduced species is on the right. So, you can relate it, it is always confusing. So, remember loss of electrons is oxidation, gain of electrons is reduction, and then you will be able to link it up. Okay. So, it is given in this form in this table. in the book, actually, I've given it in both forms because of this confusion that will arise. So here, this is the reaction that we're looking at. Oxygen is the oxidized species, the superoxide is a reduced species. So this was the half reaction that we had represented by this, right? So O2 plus E minus giving you superoxide, so minus 0.33 volts. So try to find the other reaction.
Yeah.
You found it. So you are fine with this, right? Okay. So here we have reduction potentials, standard reduction potentials at pH 7. Okay. So the reduction potential is not an extensive property, so it doesn't depend on the amount of electrons transferred and things like that. It doesn't depend on amounts.
You can't directly add it.
You cannot directly add as you add an extensive property. So we convert the information in terms of extensive properties, which we can do in terms of the Gibbs free energy itself. Okay, we have the relationship of delta G is minus NF delta E naught dash. So for this reaction, we take the E naught dash, we convert it into G naught dash, sorry, delta G naught dash, right? And then we can do the algebraic operations. Now, which part is unclear? Abbas wanted to go through it again. So, no, anything is unclear, please raise it now. So here we are looking, excuse me, at 1 mole of each. So we are all fine. We didn't have to worry too much about the conversions and so on. So the free energy change is minus 5.886 into 10 power 4 joules. That's what we are looking for, and we can express it in terms of the other units also. And the negative value from thermodynamics, we know that the process or the reaction is spontaneous. Okay. Now take 10 minutes or 15 minutes and work this out. So the information is available to you. As expected, this is not as straightforward as the previous one, but work this out. So if somebody is uncomfortable, please let me know, maybe outside the class and so on and so forth. So we'll put things out. Yeah, temperature, pressure is assumed to be 1 atmosphere. But usually temperature, pressure are what is meant by conditions for all these things. In the case of a cell, usually temperature. Pardon? Oh, what should be the thing? This is, take it as 30. Let me see what I have taken. I think it is 37 degrees C. If it's a mammalian cell, it is 37. Other cells, maybe some bacterial cells at 30, some yeast cells at 30, and so on and so forth. If nothing is mentioned, please take it at 37, but let me check whatever has been. Okay, so 10 minutes are done. First few steps. And people are working it out. Okay, you work it out. Then let's see. Yep, 37. 37 degrees C. I have assumed a mammalian, rather I have assumed a mammalian cell. Or if it happens to be a mammalian cell, that is what it will be. Okay, some steps in case. So this is one half reaction, right? The standard reduction potential at pH 7 is minus 0.18. The ferricytochrome ferrocytochrome reaction 0.26. And let us first find the standard available free energy and then the actual available free energy from that. The standard is assuming all concentrations are 1 molar except hydrogen ion concentration. So we can follow the same procedure as in the previous example with oxygen and hydrogen peroxide, but the reaction pair represents a redox reaction. Okay. So in this case, you need to make sure that those conditions are satisfied. It is a redox reaction that happens, and therefore we need to make sure that the number of electrons are balanced. first. So here you have 2 electrons, here you have 1 electron, which is inappropriate when you're looking at a redox reaction between the two. So to do that, as written, the reaction with FAD has 2 electrons, whereas the reaction with cytochrome C has 1 electron. Since we are considering the process of electron transfer from FADH2 to cytochrome C, the electrons need to be balanced. To balance the number of electrons, that's quite straightforward. Multiply the cytochrome C reaction by a factor of 2. So you get that. Okay, you multiply throughout by 2, but this note is an intrinsic quantity. This you should not multiply by. This is a standard reduction potential. You should not multiply it by the factor. Some of you are confused. Let me explain further. The standard reduction potential was left unchanged. It was not multiplied by 2. This is because it's an intrinsic quantity that I mentioned. To understand that further, recall that it is a potential difference between the 2 electrons, right? So, whether you transfer 1 electron or whether you transfer 1000 electrons, it does not matter. The potential difference will remain potential difference, right? So, that is the reason why, that is the physical interpretation of the fact that it is an intrinsic variable. Okay. That does not change with the number of electrons you transfer. So, now that you have these two equations, this is equation E, I call it the balanced equation with equation C, FAD plus 2H plus 2E minus giving you FADH2. This one has the 2 electrons, so that is fine. You balance the number of electrons. So, if you subtract one from the other, C from E, the needed process of electron transfer from FADH2 to cytochrome C is represented. So, this becomes the needed equation. Sorry, this is equation C. You do the subtraction and so on and so forth. And now you look at the standard free energies. So, standard free energies from the reduction potential NF E dash E naught dash. So, NF E naught dash minus NF E naught dash of equation E minus NF E naught dash of equation C is what you actually need, and that turns out to be 2F delta E naught dash, which turns out to be that value. Okay. So, this is under standard conditions. However, we are not looking at standard conditions, we are looking at cellular conditions where the the concentrations in the cell of the species are very different from 1 molar. So, how do you handle that? Your Nernst equation. E dash, we will have to work in terms of E dashes, and E dash can be obtained from E naught dash in terms of the Nernst equation, E naught dash plus RT by NF, ln of the ratio of species with lesser number of electrons to species with higher number of electrons. If we assume this has been happening in a mammalian cell, of course, that is an assumption. The temperature happens to be 310 K, that is 7 degrees C. For the FAD half reaction, you will get E dash as minus 0.171 volts if you do this calculation, E naught dash plus RT by NF ln of species with lesser number of electrons, and that in that particular reaction is FAD. Species with higher number of electrons is FADH2. So, you get minus 0.171 volts. For the cytochrome C half reaction, you would get 0.2453 volts. Okay. So, this is the standard reduction potential, not standard, sorry, reduction potential at pH7, which is different from the standard reduction potential at pH7. And you work with the reduction potentials, the available free energy turns out to be minus 2F delta E dash, which happens to be minus 8.033 into 10 power 4 joules. Any clarification? You had enough time to work through, so you would have gotten into it and so on. So, now any clarifications? Do not take it on face value. Okay, you would have worked it out somewhere you would have gotten confused. If the confusion got cleared, that is fine. If it did not get cleared, then raise it now. Does anybody need any of these numbers for more time? Previous, this or previous, or even before? This is fine. Okay. Any doubts? No, it might be a doubt for others also, you might want to raise it. Swati, you're fine? Yeah. Swati, you're fine? Okay.
So in the chemical reaction of cytochrome C, Fe3 plus 2, Fe2 plus E, E0 value is 0.26 volt, but
Right.
we consider the the reaction where it is reacting with FAD to create FADH2.
No, this is for the half reaction alone. This E naught dash is 0.26. That is for the half reaction alone. See, what actually happens is the redox reaction. But to be able to get better insights, the information has been broken down into half reactions, and you can assign these values nicely to the half reaction. Then you can work with these numbers. That is the reason.
But in the larger reaction, it is reversed. So won't we consider the negative of 0.26, or are we just considering this half reaction?
Now, it depends on what you do to get the reaction of interest. Here you have, so C is okay. E is this 2Fe3 plus cytochrome C plus 2E minus, giving you 2Fe2 plus cytochrome C, right. So, this is one reaction, and C happens to be FADH2, giving you FAD plus 2H plus 2E minus, right. That is the reaction as written. So, you need to do E minus C to get whatever you are looking for. What are you looking for? You are looking for transfer of electrons from FADH2 to cytochrome C. So, it depends on what you need. So, addition and subtraction will depend on what you need. I mean, yeah, don't go blindly by the last problem. We needed to add them to cancel them out, right? Or rather, we needed to add them to get the final reaction. In this case, you need to subtract. So, it depends on the need in your situation. So, whatever you do to the reactions, you do to the delta G values. Yeah, please clarify these things. These nagging doubts, don't assume, don't accept and go forward. Then you'll always be confused. Any other numbers needed?
Okay, so this is for 1 mole of the.
Yeah, under standard conditions. So, all reactants are present at 1 mole concentration is the assumption. Whereas, in a real cell, they are far away from 1 mole, 10 power minus 6 and so on. So, you use the Nernst equation to convert to get the value at the concentrations that are involved from the standard values. So, you need the temperature for that. So, okay, fine. Any other questions, comments? So, this is how you use the information. That's essentially what we are looking at to analyze the reaction to get how much energy is available, and this you could use it whichever way you want. It depends on the purpose. Those purposes could be widely different. So, that's the beauty of having fundamental information. So, you can use it the way you want. Right? Okay. Good. Yeah. Any other question? Good. So, if no questions, then we will move to the B part of chapter 2, going at quite a good click. How long has it been? We started 17th of, no, actually we started 19th of Jan or something like that, right? Less than 15 days, not bad. And that too, we didn't have quite a few classes in between. Very good. Okay, some continuation of that. Earlier we saw thermodynamics, now we see some kinetics. We look at the, we refresh our memories with the first few slides. Kinetics is the other important tool apart from thermodynamics that is available to us for analysis of reactions. It's a strong pillar of analysis. Some concepts review. You all know what rate is. Rate refers to the speed of a reaction or a process. It has instantaneous connotation, although it could be measured in different ways. Okay, please understand this very clearly. The connotation is instantaneous, but it is measured in very many different ways. And also the rate is usually normalized. Okay. The normalizing factor could be the relevant volume per unit volume, the relevant area per unit area, the relevant mass of a certain species, maybe a catalyst species, maybe some other species, and so on and so forth. Okay. So, typically the rate is represented as a normalized value. So, rate is change in the amount of species per time divided by the appropriate normalizing factor. You might want to write this down to clearly understand what we mean by rate and its representation. Just the last part of it. The rest is we are revisiting it and making sure that we understand the important bases. Okay. Also note the people who have done transport will know this already. Let's repeat it. It's worth repeating. In chemistry, right from chemistry, we always said dc dt is the rate of a chemical reaction. Okay. Be a little careful with that. Okay, because in the overall scheme of things, that's not always the rate. The rate has a separate concept. The reaction rate is not always equal to dc dt. dc dt is the rate of change of concentration in the system. Okay, time rate of change of concentration of that species in the system. Therefore, it is an accumulation rate, right? You know that mass conservation is fundamental, and you recall input rate, output rate, generation rate, consumption rate, accumulation rate from the concept of mass balance. Okay, that's the other video that I had given you in case you didn't have a background. The others who have a background just need to recall that. They also may not have understood these in those terms, although we did emphasize that quite a bit in the transport course. Okay. Here. And I didn't realize that I had that here. Input rate plus generation rate minus output rate minus consumption rate is the accumulation rate. This you can close your eyes and write as long as they are not nuclear reactions or there is no motion at the speeds of light. Okay, when there is motion at the speed of light, there is mass dilation and so on and so forth. So, those two conditions are ruled out. And in all the other conditions, you are not considering nuclear reactions where there is mass to energy conversion. As long as these two things are not done, then this equation you can close your eyes and write at any point in time. Okay, that's the power of what we did in transport. Those four basic things you can close your eyes and write. Okay. Okay, so accumulation rate, which we represented as mass change per time d dt of m, or in terms of the concentration, because concentration is more easily measured, volume times the concentration divided by rather d Vc by dVc dt, okay, d dt of Vc. Any questions on this at all? Fine. The strategy used to measure the reaction rate is to measure the concentrations of a relevant species, typically the reactant or the product. Reactant will be like this, product will be like this. Reactant of a relevant species, a reactant or the product in the reaction, at various times in a well mixed vessel operating in batch mode. This is the way typically we measure reaction rates, if the reaction rates are in a reasonable time that we can measure, okay, or in a reasonable range that we can measure. If the reaction rates are too high, then you cannot use this method at all, because taking sample will take time, measuring the concentration will take time, and so on and so forth. Okay. So, for appropriate reactions, you in this typical chemistry lab thing that we did in 11th standard, 12th standard, you take a vessel, you add everything, then starting from 0, you measure the concentrations, then you process the data to get rate, to get the initial rate typically. Okay. When you do this and you write the mass balance, this of a species over a system, the net production or the consumption rate of the species equals the accumulation rate. Okay. That is why we typically use dc dt to represent rates going by the standard way of measuring reaction rates in a lab. Okay. That is the okay, let me take it a little further. Oh no, okay. See, if you have a batch system, there is no input rate, there is no output rate. Right. So, the generation rate minus the consumption rate equals accumulation rate. So, if you are following the reactant concentrations with time in a rate measurement experiment, you do not have any generation of that reactant. So, minus the consumption rate equals accumulation rate. This is where the minus comes from, minus dc dt. We always write minus dc dt and so on and so forth. This is where it comes from. Then minus is not inherently associated with anything. You write it from a material balance on that system, which is fundamental, the minus pops out. Okay. So, in a batch system, you can say that the accumulation rate equals the reaction rate if you follow that process, otherwise no. Then rate law for review, it is a mathematical expression relating the reaction rate to the species concentrations typically, and because the concentrations are usually easy to measure. So, typically the rate is written as a constant times the concentration of species raised to an index n1, concentration of species 2 raised to an index n2, and so on and so forth, right. And K is called the rate constant, n1, n2, and so on and so forth are orders with orders of the reaction with respect to that species. Any questions, comments so far? Well, fine. Okay. So, I am just brushing through the information that we all need to be clear about. And the overall order is nothing but the sum of the individual orders. Okay. Now, so far review, hope that all the principles have come back, you have been able to recall the principles. Now, let us start looking at some reactive species reactions in the context of something called an initiation reaction, something called a propagation reaction, and something called a termination reaction. Where have you seen this terminology before? Chemistry, where? Polymer synthesis, yes. Where else? Okay. Protein synthesis, organic chemistry. Protein synthesis where?
No, the protein synthesis is a 3-step process. Translation.
Oh no, that is translation.
3 steps, right?
3 steps, yeah, but that's a different process. Yeah, that's a different, that's a biological process. Yes, yeah, slightly different terminology. Yeah, organic reactions, yes. Okay, and if you recall, I mean, if you figure out the commonality of wherever you have learnt all these, you have learnt all these in the concept in the context of reactive species involved reactions, free radical involved reactions. Okay, so all free radical involved reactions, this is a nice framework for a certain reason, which I will tell you a little later. Okay, whenever you're dealing with free radical reactive species reactions, trying to look at it in terms of initiation, propagation and termination reactions is a nice way to look at it. Yeah, relevant for free radical reactions. This just provides a basis to analyze the free radical reactions. However, recall that not all reactive species are free radicals, only some of them are free radicals. Good. Okay. What I'm going to do next, I think I'll start it in the next class. I have one more, I have no minutes left. So, I'll start this in the next class. We are going to look at some popular reactions among reactive species reactions in this context. Most of them, but I mean, all these would be free radical based reactive species, and then we look at some other reactions. So, this is just to get you familiar with some of these reactions, so that you don't feel lost when you come across them. Okay, that's the idea. We'll do this as quickly as possible. Any quick questions? I realized that clock is about 3 minutes behind. So, if I need to stop, other I mean, now it's lunch, but if it's the next class and so on and so forth, it becomes a problem. Okay. Any quick questions? We'll meet next on Thursday at 10. See you people. Lecture videos, unlikely. Unlikely because I haven't processed them. I'm not going to process them till the book comes out. Is that way I ensure that it doesn't get into public domain before the book comes out. The book is coming up. But the this thing, Halliwell and Goodrich is available. 3 print copies are available in the library.
No, I searched, it's not there.
Somebody has taken it
I
away.
searched.
Then go for the online version.
How to like?
Click on that.
It's not there.
It will do that.
Print version was okay there.
Click on this. Click on this. You'll certainly get to the online version. Okay. The library has bought it. Krishnapriya made all efforts, and students have referred to it earlier. So, and I definitely know that it is available. If not, check with the library. With the information that I've given you on the Moodle page, just a click should be fine. You should be able to reach that. If you're not able to reach that, check with the library. Did anybody manage to reach the e-copy of the book? You're done. So,
I mean, you need to just have that VPN or something set it, like it should be connected to the intranet of IIT.
you'll have to access it from inside the IT. Otherwise, you won't get it.
Then you can access.
You can download the book, by the way. You can download the book because I mean the library has paid for. I mean, the institute has paid for it, so you can have full access to it anytime. That's this is Halliwell and Goodrich, but beware, it's a Bible. It has everything in it, and we are not covering it in any order as in the book. I'm just picking up right from first chapter. I'll go to the 16th chapter and so on. So